Again, it's a great honor to be here giving these lectures. Can you all hear me? And thank you so much for coming back today. I must have done something okay. One thing I know I did okay, the plumbers. You know who I'm talking about. You know who you are. So, they really like being called the plumbers. Although I noticed that the drains in my room this morning were all clogged up. I wonder if somebody could go take care of that. It's okay. So the other thing that Leon called me, I think I can say it here, was a half astrophysicist. So this is part two. So in part one, we kind of warmed up. We started out with the simple universe, the Big Bang, just having galaxies. And today, let's see, what do I call it? From simple to rich and interesting. Because when we did the focus groups, the word complicated didn't poll well. So it's going to be rich and interesting today. And so if you remember where we left off last time, in this simple universe, we had Alan Sandage, one of the truly great astronomers, talking about cosmology. And back then, there were only a handful of cosmologists, maybe 30 in the world. And he had the foresight to devote his life to this impossible task of the universe. H naught, the expansion rate, and Q naught, how much it's slowing down, and then it would all be done. And then by this marvelous telescope, the Palomar telescope, The Perfect Machine, as a book called it. That's a wonderful book that if you have a chance to read it. And I thought I would show this picture. So one of the numbers, so I'm going to go slightly out of order today, but I'm trying to tell a story, but this one will be a little out of order since Sandage ordered that one of the numbers be measured better. That was H naught, the rate at which the universe expands. That's probably the most important number in cosmology because the inverse of it tells you the age of the universe. If you know how fast it's expanding, then you know how long it took to get there. And this is the number that Hubble got 500 for. And don't worry about these units. And it took the Hubble Space Telescope and allowing women into astronomy. So for all those years, we kept them out. And for the ladies in the audience, this was not personal, it was a business decision. Women are smarter than men, and we knew once we let them in, it would just be over for us. And so this project called the Hubble Key Project that used the Hubble Space Telescope to measure the Hubble constant was led by Wendy Friedman at Alan Sandage's institution, and there's interesting stories about the friction between them. And let's see, Wendy tells the story that he was her mentor because he tormented her because of the rivalry, good honest rivalry. But so they actually measured this most important parameter. And you don't have to worry about the error bars. That's for the physicists here. Physicists like error bars, and so we thought we'd really impress them by putting 2 error bars on it. And just to give you the sense of how much the instrumentation and the measurements of the universe had changed, all of Hubble's data would fit in that first little box there. If you remember, the galaxies that he saw that were moving the fastest were moving about 1,000 kilometers per second, and this goes up to 30,000 kilometers per second. And I made the joke about Hubble being famous because he could look at a scatter plot and draw a straight line through it. And here, there really is a straight line. And so this was a real achievement, measuring this number one fundamental number, the expansion rate. Okay, and then we talked about Penzias and Wilson, and this was kind of the beginning of the rich and interesting universe. They found these microwaves that are the heat left over from the Big Bang, the hot Big Bang. And then we talked about a universe that was hot, simple, it cooled, and layer upon layer of structure was laid on. So a nuclear reactor, and one thing I think I forgot to say last time is that this is where the helium in the universe is made, the little bit of deuterium. The rest of the elements are made in stars. And Gamow sort of accidentally discovered how that worked, and it was Hoyle who actually also gave the Page-Barbour lectures that really spelled it out. And then the atoms formed, and then the light, the microwaves. What I didn't say is that the microwaves come from a redshift of 1,000. They come to us when the universe was 1,000 times smaller. And just more for the gee whiz, because cosmology is so exciting. These microwaves that we detect today, when they left, were actually optical light that you could see with your eyes, and then they've been redshifted into the microwaves. And now, do not enter. What was that all about? So that's what I want to tell you about now, and that's kind of the revolution Hank was telling you about that happened around 1980. First I need to say I want you to know the successes, and then in science, evidence is important. So we talked about that last time. A theory being cool and beautiful is not good enough because we got the plumbers checking us, and so sometimes the ugly facts. The success. This is really one of the remarkable accomplishments of the 20th century. A physics-based, a reality-based history of the universe from 1/100,000th of a second to today, 13.7 billion years later. That's pretty good. In fact, you might say, do you really need to know about that first? Okay, the evidence. Evidence is very important. So this is not just a good story, but just to review the evidence, the expansion of the universe, the cosmic microwave background, the amount of helium left over from the Big Bang, we call that Big Bang nucleosynthesis, and the general idea and the general concordance of the idea that gravity is the master builder. It takes a lumpy universe, tiny lumps, 0.001%, we'll come back to those, and turns it into the structure that we see. The big questions were, is the universe going to expand forever, recollapse? How much matter is there? That's the Q-naught question. Where did the heat come from? Actually, you guys were really good. Yesterday, you asked these questions. Where did the heat come from? And I convinced you that the universe in the beginning was very smooth. We're going to talk a lot about that. Why is it? What is the? We don't do why. What is the origin of that? The origin of the small lumps. The universe was slightly lumpy, and the numbers that describe the universe were not very well known in, this should say 1970. So Wendy and her team didn't make that measurement until the late 90s. So certainly we didn't have numbers to back up this picture. And the real limitation, you all know about the Berlin Wall, right? Don't they teach that here? But do they teach the Hadron Wall? So the real limitation in cosmology was the Hadron Wall. That's the origin of the do not enter. And one of the most influential books on cosmology at the time was written by Steven Weinberg, called Gravitation and Cosmology. And he talked about why you can't talk about the universe when it was very, very young, when it was younger than 10 to the minus 5 seconds. And the Hadron Wall prevented you, even friendly guys like me, from speculating why. And the reason was simple, that the universe at early times is smaller, and when you get down to 10 to the minus 5 seconds, the neutrons and protons are on top of one another. But there's more. And the forces between the neutrons and the protons are very strong. So what do they do when they're on top of one another? But there's more. When you raise the temperature higher than that, there's all kinds of additional particle states that Brad Cox and his friends were discovering at the big accelerators. And so I think the technical term for it was a mess. And so you really, don't even think about going there. And now, do you all remember when the Hadron Wall fell? So in 1980 was the fall of the Hadron Wall. And this involved experiments, and this is a theme that we're starting to see this theme that Hank was talking about, that we not only use telescopes to explore the universe, we use accelerators. And so this is the 2-mile-long linear accelerator in Geneva, Illinois, just outside of Chicago. Oh, actually, I think it's in, where is it, Brad? It's at Stanford. Sorry. Well, you know why God created time. So think everything doesn't happen at once. You know why he created space? So not everything happens in Chicago. So this is the Stanford Linear Accelerator, and they did an experiment that was thought to be so unimportant that the lead experimenters for it were sort of, you're picking straws out of the hat or whatever it is. Nobody wanted to do the experiment, and so a couple of guys got left doing it, Henry Kendall and Jerry Friedman, and they were aiming electrons at neutrons and protons, and it was thought to be so boring that only assistant professors at MIT would do it. And they discovered something quite interesting that changed the course of particle physics and changed the course of astronomy, that inside the neutrons and protons were small bits that we now know as quarks. So they discovered that neutrons and protons were made of smaller bits known as quarks. And then this is a purely technical thing, because the theorists are the smart ones. So the theorists proved that the force between quarks when they get really, really close together vanishes. And when the quarks get far apart, the forces get very large, which is why we don't see free quarks. But what that meant was that when you mush the universe together, that's a technical term, that you just get quarks, and these quarks, the number of quarks that condense on the head of a pin is infinite. So they're point-like particles, the forces between them are small, and so all of a sudden the early universe is open for business. And all of a sudden, we have this picture of the early universe, it began from quark soup. A soup of fundamental particles where we can actually do some speculating. And so all of a sudden, this 10 to the minus 5 seconds was open. So now here I come along, 1980, I go to the University of Chicago, and again, they're handing out research projects, and they say, well, all that's left of the universe is the first microsecond, so that one's yours. And thinking that would be pretty uninteresting. But so we're now going to talk about the events that happened during this first microsecond and how they shaped the universe that we see today. And and just this is for you to think about. So this is a full-scale model of all that we can see today when the universe was very young. So remember, all that we can see today is really big, billions and billions. And when the universe was very young, this was the size. And it was just this of all that we can see today. And so that's how the universe began. So now I'm going to segue into what Hank was talking about. So this period in the early 80s, there were all kinds of ideas from particle physics. So this diagram here we are today, so it runs a little differently. Here's the beginning. So this is the complete history of the universe. You can see the quarks, you can see the neutrons and protons, you can see Big Bang nucleosynthesis. So this one's a little more linear. All of a sudden, we're open for business. And there were ideas in particle physics. To be fair, the particle physicists thought that they could construct theories that unified all the forces.